the notations on group. So we have a semi-simple group, we have Borel subgroup, and we have maximal torus. And then we define R as the set of roots. And we have R dual, the set of co-roots. We also have S, so the set of simple roots. So it's a basis of the positive roots. So all these sets are finite. We also have a finite group, which is the Weil group. And the Weil group is generated by some simple reflection with alpha in S. And what I should also recall, yes. And so we have the fundamental weights for simple roots, so indexed by simple roots, which is the dual basis of the co-roots associated to the simple roots, so the simple co-roots. So maybe let me redraw the picture for SL3. So we have alpha, we have two simple roots, alpha and beta. Here we have alpha plus beta. In that case, we have alpha equals alpha dual and beta equals beta dual. And the fundamental weights are this one and this one. So here I represent so the picture in R2 with the canonical scalar product, and with this product, so I have I suppose that we have the scalar product of alpha is equals to 2, so it's also for beta it's also the case, and then alpha dual is defined by 2 alpha over so the scalar product of alpha for this is for all. So maybe just so for all gamma in yes. And if we draw the picture for S05, or which is similar to SP4, and then so we have this picture. So we have alpha here, we have beta here we have alpha plus beta, and here we have 2 alpha plus beta. So in that case, so we suppose that alpha equals 2, but in this case we have beta equals 4. So with this, and we have also the definition here. So we will see that so by this way the pairing is not symmetric. So in this example, so it's just a remark. And in that case, so we are alpha equals to alpha dual, but beta is 1/2 times so beta, so the alpha of beta, and then alpha plus beta is equals to omega beta, and we have omega alpha here. Okay, so that's a general picture we can have with the root system. So now I want to speak about dominant weights. So K is a dominant weight. So it's a definition. If we can write chi in, so I don't say it, but so omega alpha is the basis of the characters of T. So if we suppose that G is simply connected, so we can always write so chi as a sum of omega alpha with coefficient, with integer coefficients, and so chi will be dominant if the coefficients are all positive, so or null or equal to 0. So with alpha in so positive or 0 coefficient. So this is the definition, and the proposition. So maybe I can. So all positive of dominant character will be here, and we call this cone the dominant chamber. And here we have this cone. So a nice property of this dominant weight, it's that the simple G modules of so simple G modules is in bijection with dominant weight. And in particular, so we have chi, we associate. So I don't construct this map, but I just want to say to explain a nice property of the simple G module associated to dominant weight, and so a nice property is that there exists a unique V chi in V chi up to a scalar. So non-zero vector. So we have a vector such that for all elements in the Borel subgroup, we have that B acts on V chi as the multiplication by chi of B on V chi. So this is the action, and this is the multiplication. So this is an element of C star. And then so V chi is an eigenvector, so we call it so V chi is called the highest weight vector, of weight chi, and V chi is called the highest weight module, highest weight module of highest weight chi. Okay. So maybe so it's sorry, it's a module of highest weight chi. Oh, right. Chi of V, chi is a weight, so chi is a map from the torus, so from B, in fact, to C star. So I said that weights are weight from T to C star, but in fact we can extend so the characters of this function to the Borel subgroup. So if you look at SLN, you know that the characters or the fundamental weights of SLN are just we just multiply so in SLN. So we have so omega alpha I of a diagonal matrices with T1 Tn is just T1 times Ti, And so we see that we can extend this function to upper triangular matrices. So it's well defined. It's a morphism of algebraic group. So we can extend characters to the Borel subgroup. And in few cases, in fact, we can also extend the characters to parabolic subgroup. So for example, omega alpha I is also so Z omega alpha I is a set of characters of which I call PS minus alpha. So it's maximal parabolic subgroup. So for SLN, for example, so we take so and you see that omega alpha I can be extended to P to such matrices, can be defined to such matrices as a determinant of the first block. So here omega alpha I is the determinant of the first block. And so instead of calling this maximal parabolic subgroup PS minus alpha, we also call it very often P of omega alpha I, because it's maximal parabolic such that omega alpha I is a character of P, and not only of T. Okay. So we can describe all simple G modules, and in each G modules there is a particular vector which is called highest weight vector with this property. So this description is useful when we want to realize flag varieties as subvarieties of projective space. So now so let's take chi, so a dominant rate. And then we can define x at so the orbit of v chi in the projectivization of the module of highest weight chi. So and then x will be isomorphic to G mod pi with I equals so the set of alpha in S such that I think so it's chi alpha dual is equals to 0. So for example, so let's take SLN. So we have omega alpha I is just so the exterior product of I times of Cn, and the highest weight vector will be so E1 EI, where so E1, so we choose a basis. So when you write, so when we say that the Borel subgroup is the upper triangular matrices, we fix a basis to write the element of SLN into a basis. So this is this basis. So the basis used to write the element of SLN as matrices. And in this basis, so we can see that it realizes this property. So just at E1, it's associate T1 B11 times E1, and E2 it associates something times E2 plus something times E1, and so it's an exercise to check these things. And so in this example, so we can take chi as the fundamental weight omega alpha I, and look at what we obtain. So we have okay, so we take this, and so we look at SLN times E1 EI in the projective space, and in fact we obtain the Grassmannian of high-dimensional subspace in Cn. And this is a plucker called the plucker MLA. So it depends on the. So here we obtain also polarized varieties, because it depends on the character we choose. So here we choose omega alpha I, but we could also choose 2 times omega alpha I, and so we will have another embeddings which correspond to another ample line bundle. So in this example, the line bundle is the line bundle who generates the Picard group. So the Picard group is of rank 1 in this example. Okay, so now I'm finished with flag varieties. So I want to generalize what we did for toric varieties and flag varieties to define more general varieties. So this is the second part. So spherical varieties. So first let me give the general definition. So a normal G variety. So when I write G variety, it's a variety with the action of G. So G variety is spherical if there exists a Borel subgroup such that B has an open orbit in X. So we already saw yesterday that so for flag varieties it is satisfied. So we already saw that flag varieties has an open orbit on under the action of a Borel subgroup. So example of spherical varieties are flag varieties, and we are also have toric varieties. And for toric varieties, so we have G equals C star to the power n, and it's also equals to the Borel subgroup. So maybe I just say a remark. So for flag varieties, we have supposed that G was semi-simple. So it means that there is so its center is finite, but we want also to, so C star to the power n is not semi-simple, but it's reductive. So we suppose here that G is reductive. So for example, we have a G ln, which is not semi-simple, but reductive. And so GLN can be write as So the product of C star times SLN. So it's not a direct product, but it's a product. So and SLN is called the semi-simple part of GLN. And more generally, we call G mod RG. So where RG is a radical of G. So I don't write the definition, such the connected, closed, and solvable and normal subgroup of G. So in the case for the definition of semi-simple is that the radical is trivial, and for reductive the radical is not trivial. So we have a radical. So here which corresponds to C star, so to the diagonal matrices with the same coefficient in the diagonal. So and then so what you just have to understand is that to understand or to know is that so there is the same combinatorics. So we have the root system of G will be the root system of the semi-simple group. So it will be as before. So G is the root system of a G mod RG. So the semi-simple group associated to the reductive group. The only difference is that there is more characters. So only difference is that there's more characters. There are more characters. So for example, so the most easiest example is C star at the power n. So the semi-simple group of C star at the power n is 1. So it's so here it's G C star at the power n mod R of C star at the power n. So so here we have no roots and no co-roots. So but we have characters. So we have all characters of C star at the power n. And another example maybe it's so for GLN. So we have SLN as a semi-simple group. So we have all characters which are generated by omega alpha for alpha in S. But we have also another character which corresponds to the character of the radical here, G, so of C star, which is simply the determinant. So it's a character of G. Okay, so we have additional characters. But so if you are lost, just think of toric varieties. So for toric varieties, we have no roots, but we have also characters. So we have to take in account the characters here. And for general groups, so it's a mix between both situations. Okay, so it's just a technical point. So don't worry if you don't understand this. It's not very. So now. Okay. So now I want to say that so the divisors which are stable under the Boris group play an important role in the theory. So we have seen that for flat varieties, so the Schubert varieties of codimension 1, so generates the Picard group, and so they play an important role. And for toric varieties, we also have seen that the C star n stable divisor corresponds to the edges of the fan. So they also play an important role. So in our case, so we have, so maybe I just have to say, so if we have a remark, so a spherical orbit, a spherical variety, sorry, has a G open or an open G orbit. So it has an open B orbit, but it also has an open G orbit. So it's bigger than the B orbit, the open B orbit. And we call it G mod H. So it's an homogeneous space. We call it G mod H. And so then we have, so if we take X, so we have G mod H, open orbit in X, sorry. And so now we can look at the B stable divisors of X. So what are the B stable divisors? So we have two sorts of B stable divisors. We have the divisor which are in fact G stable. So here the irreducible divisor. So there's always irreducible divisor. So G stable divisor, and we will have also the B stable but not G stable divisor, and this divisor which are not G stable will come from the B stable divisor in G mod H. So we have the B stable, so the closure in X of B stable irreducible divisor of G mod H. So if we look at the example of toric and flag varieties, so we see that for toric varieties, so we only have a G stable divisor because G equals B. So we only have the G stable divisor. Which corresponds to the edges of the fan associated to the toric varieties. And for flag varieties, there's no G stable divisor. Because X is homogeneous, and but there is so this divisor are called the colors of G mod H or X. So no, of G mod H. Sorry. So they are called the colors, and here we have the colors are corresponding to the Schubert varieties of codimension 1. So now I would like to classify, so I will fix G mod H, and the aim is to classify all possible X, so all possible G mod H embedding. It means normal varieties with open orbit isomorphic to G mod H. So I fix G mod H spherical. If G mod H is spherical, it will be also X will be a spherical because the definition so only depend on the open G orbit. So the open B orbit will be necessarily in the open G orbit. So this is the aim, and this is classification due to Luna and Wust. And there is also papers of Brion and Knopp about these things. So, but to explain this classification, I will first restrict to a simpler case, which is the orospherical varieties. So what's the definition of orospherical? So I will say that G mod H or X or is orospherical, or H also. Orospherical. If so, we have several definitions. So we can say that G mod H is a fibration on a flag variety G mod P, and with fibers, all fibers isomorphic to a torus. Another definition is to say that H is the intersection of n of the kernel of n characters with chi I from P to C star. So morphism of algebraic groups. So characters of P. Okay, so, and we have also a third equivalent definition, with, but I will not give it here. So two definitions are enough. So we see that so there's a mix between toric varieties and flag varieties. So maybe first example, it's flag varieties with n equals 0. So here we have G mod H equals G mod P, and toric varieties. So we have a G mod P equals a point. So P equals G, and equals C star to the power n. And n is the dimension of the variety. And so maybe I just said that n is called the rank of G mod H, or the rank of X. So the ranks of the system. And with this definition, I can also say that P is necessarily the normalizer in G of H. So it's a set which stabilizes H by conjugation. And so it's if we fix H, P is automatically defined by the normalizer. So it's defined, and then so we have several definitions.
This P is that P. Right?
Yes, this P is that P. So, and also that P. So all these P's are the same. So for one fixed G mod H. So maybe I can give. Maybe I can. So I can give other examples, and so there's a mistake on my slide. So it's not orospherical varieties, but orospherical homogeneous space. So it's not. So it's just the G mod H described here. So some example of G mod H. So the first line is correspond to toric varieties. So we have the rank, and the dimension is the same. The second line is for flag varieties. So we have a G mod P, and so the rank is 0, but the dimension is the dimension of G minus the dimension of P. And another example is SL2 mod, the triangular matrices with 1 on the diagonal. And here we'll see that the rank and the dimensions are not the same. And the third last examples are examples where the rank is 2. So we have n equals 2, but the dimension can be large, as large as we want, in fact. So we can find, we can always find example with as large dimension as we want in fixed rank. So we will classify the varieties of very big dimension with combinatorics in small dimension. So the rank will correspond to the dimension of the fans, of the colored fans. So I will explain this later. So it will correspond to the dimension of the combinatorics we look at. Okay, and so the third the definition of orthogonal is to say that H contains a subgroup like this. So U is the unipotent radical of Borel subgroup. So it's the third definition, but if you don't know a lot of things about algebraic group, it's not necessary to know this.
What is my dimension?
The dimension of G mod H as varieties, as a variety. So G mod H is a variety, and so the dimension of G mod H. Sorry? The complex dimension, yes. So all my work, so all my talk will be on other C, so other complex fields. Even if so the theory of Luna and Wust is also true in arbitrary characteristics, so it's due to Knopp. So Knopp generalized the theory for in algebraically closed field, so in any characteristics. But I will always talk of varieties of complex fields. Yes, orthogonal is spherical. Ah, yes. Maybe I mentioned this. So remark. Spherical implies spherical. Because so we have an open B orbit here, and when we take the inverse image of the open B orbit here, it will be also an open B orbit. It will be also an orbit, an open B orbit. Okay. So now I want to define the colors of orthogonal varieties. So we can already define colors as so we in G mod P. Recall that we have colors inside them. So we have the Schubert varieties of code dimension 1, and so I have this map here, G mod H. So I can take, so I denote it by pi. So I can take pi minus 1 of x w0 s alpha, and it will be B stable, irreducible divisor of G mod H. And I call it D alpha. And this for all alpha in S minus I. So for flat varieties, we are all this for all alpha in S minus I. So for all such alpha, we can have this one. And the fact is that by this way we have so the set of colors of G mod H is equals to the set of D alpha with alpha in S minus I. So we have a description of all bistable irreducible divisor in G mod H. So in the situation of overspherical variety. So that's the first reason why the theory is more simple for all spherical varieties than in spherical varieties. Because for spherical varieties, so the description of colors is not so nice, and so in fact we don't have a general description of colors in the general case. So so case by case we can describe them, but not in general. So for all spherical varieties, we have a nice description. And so what I should say now? Yes. So another nice property of all spherical varieties is that we have some particular characters here, which define the H here. And in fact, so we have a lattice which is generated by the key I, and so lattice so is isomorphic to z at the power n. So so it's a sublattice of the lattice of characters of the torus of G. So it's sublattice of the character group given by chi. So we have a lattice of rank n, so the rank of the variety. And what else? So and we can also define. So we also define the dual of M. So so homomorphism Z of M. Dual of M, and I will also denote by this the pairing between N and M, and I will also define so the R so MR on NR, so it's the vector space generated by M. So remember toric varieties, so we always have Zn included in Rn. So it's the same thing here. So the difference between overspherical and toric is that we have some colors. So we have these colors here. So we have to understand these colors inside inside the lattice n. So we have to look at these colors inside the lattice. So for overspherical varieties, so we have this is in bijection with S minus I, so it's in bijection with a subset of simple roots. And so we can, for all alpha, so for all colors, so correspond, and we have a simple root, so we take alpha in S minus I. And then we can, so alpha is not necessarily in M, but if we look at the dual of the co-roots associated to alpha, so the alpha dual, so it's a morphism from chi to so it's a homomorphism from chi to Z. So we can restrict it at M, and then we have a morphism from M to Z, and this is N. So for all alpha, we can associate a point of N. So which call this the image of the point, so the image of the color. Okay, so maybe I try to explain why we chose this point particularly.
corresponding to whole spherical.
Uh,
Even a reductive group G.
Given yes, so you can classify all spherical space. Yeah, H you can have, yes. So it's just so you describe so you fix P. So the parabolic subgroup containing Borel subgroup are classified also by the subset of S, and then just take the lattice M. The lattice M, M and I. So M and I classified. So
my question is not.
this is mesomorphism. So it's a classification of spherical.
My question is
No.
parabolic group. We know what it is. You can say that it's a subgroup containing Borel subgroup.
Yes.
What is H?
Ah, H. Okay. So
Just say
okay.
one
So H. So H is all spherical. So it's a third definition. I didn't want to give. So it contains a unipotent radical of B. Of B of a Borel subgroup. Yes, not necessarily the B we fix at the beginning, but so it contains a unipotent subgroup of B. So if B equals the upper triangle matrices, then U is the upper triangle matrices with 1 on the diagonal. So this is the third definition of spherical. Okay. So yes, so I would like to explain where does this thing comes. So first, yes. So let me consider the rational function on G mod H. So the field of polynomials on G mod H, and we look at the semi-stable points by the action of B. So it means the set of F in C of G mod H such that there exists chi in so there exists a character of the torus such that for all B in the Borel subgroup we have B of F equals of 2 chi B of times F. So G acts on G mod H, so it also acts on the function on G mod H, and then this action. So we define this this set as the function which satisfies this property. Okay, and so we have a map. In particular, we have a map from this to -0 to M to chi. In fact, and so we can quotient by C star. So we will have the same weight if we replace F by a scalar of F, so scalar times F. And the proposition of is that this map is in fact goes in fact in M, and it is an isomorphism. So maybe I just prove the injectivity of this map. Because here we see the why we choose this definition of spherical varieties. Well, so it explains the definition of spherical varieties. So So if we take f1 and f2 with the same chi, so the same weight, then f1 of the f2 is of weight 0. So it means that so it's stable under the action of B. It means that it's constant, which implies that f1 over f2 is constant on every B orbit. And so in particular, it's constant on the open B orbit. One, so it's constant everywhere. So that's why we chose to, in the definition of spherical variety, that there is an open B orbit. So to say that there is no multiplicity in the fields of a rational function of so it's a property of a spherical. So spherical implies that so X spherical is multiplicity free. So it implies also that so also if you look the section of any line bundles, it will be also multiplicity free. And in fact, we have an equivalence here between the multiplicity freeness here and the fact that X is spherical. So and we will use these facts. So for every chi, we only have one function up to a scalar, which corresponds to this chi. And multiplicity free, yes. So C of X or H of X of L is so can be decomposed in the sum of chi in the chi plus, so I denote the dominant weights by chi plus of simple module of weight chi, of highest weight chi, and usually you have here you have multiplicity ni, and multiplicity free means that the ni are equals to 1.
Decomposition
It's a n chi. In G module, yes. So it's a decomposition in G module. It can be also 0. Is simply connected. It will all for G simply connected. All line bundle will be G linearized. So now we have this map. So we can look. So we can, when we have a divisor D. Divisor of X of G mod H. So I just remark that so the rational function of X and the rational function of G mod H are the same because G mod H is open in X. So I take a divisor and I can associate so a variation VD. Which So from C of G mod H to Z. So of a function, it associates the degree of 0 and poles. 0 are poles of F along D. So it's a variation. So it means that F1 plus F2 is more than, so it's a definition, more than the minimum of variation of F1 and F2. The variation of a product is a sum of variation. It's a variation. And the variation of a constant, so on C, is equal to 0. So this is the definition of variation. So we have a variation like this, and then we can restrict it to the semi-stable function by the Boris subgroup. So minus 0, and we can also, so if we want quotient by C star, by the C, sorry. So here it's C star, yes, because we don't take 0. And so it gives so via this isomorphism, it gives a function. So sigma from divisor, so B-stable divisor. So here I set a B-stable divisor. To take this, I must take a B-stable divisor. So we have sigma, a B. So from the set of B-stable divisors to so a variation is just a function from M to Z. So it's a point of N. So in particular, we have sigma from this. So I call it the set of colors to N. And in the Hausdorff case, so the colors alpha are sent to alpha Chech M. So the restriction of alpha dual M. So the restriction of the coroots at M. So this is I will not prove this fact because it uses a representation theory, and so just admit that we have a nice description in the Hausdorff case. Okay, and so we will have also for G-stable divisor, so the divisor outside the open orbit, we also have a map. We also have a corresponding element in N. Maybe just a remark is that in general sigma is not injective. So this afternoon I will continue to explain these things, and I will give the definition of colored fan. So we have all that we need to define colored fan, because we have two lattices, so M and N, and we have the colors and the map sigma from the set of colors to N. So we have a lattice N with particular points which correspond to the color. And then, so it's not difficult to define a colored fan. And I will give the correspondence between colored fan and G mod H embedding. And And then I'll explain how to generalize this to all spherical varieties. And if I have time, I will do an example, so several examples, and study in detail the example. And if I don't have time this afternoon, I will do this tomorrow morning.